Okay, so now that we have solved an example for calculating the gain of the amplifier, let's talk about input and output impedance, or input and output resistance. These are also AC parameters, and we have to actually calculate them based on the small signal AC analysis circuit. So we've talked about the importance of these parameters when we were discussing BJT amplifiers, but it's good to review them. So let's say that I have an amplifier A. Generally, it receives its input signal from some sort of signal source, let's say V signal, and I want to actually have my signal as a real signal source, meaning that it has an internal resistance. So R signal, and I have my V signal. At the output, I'm connected to normally a load. I'm going to show that load with the resistance. That load could be the speaker that we have talked about it before, and the signal could be the microphone that we always had. So this could be microphone, this could be speaker, and so many other things. Now, um, from the standpoint of the signal source, my entire amplifier, the signal source doesn't care what is happening beyond this point, right? Beyond this point, it could be a single resistor, could be an amplifier, or could be a million of transistor that I can actually model all of them with a simple resistor, which I'm going to call Rn. So basically, if I know how much resistance I see from the input of amplifier to the right, I can replace the entire circuit here with that resistance, right? So basically, from my signal source point of view, we have a situation like this. We have the V signal, we have the R signal, V signal is connected to ground, and then I have this resistor called Rn. Now, the input of my amplifier, this point, in this circuit becomes here, right? Right after the R signal. Therefore, I can easily say that whatever comes to at the input of my amplifier, let's call that point X, Vx is going to be equal to Rn over Rn plus R signal times V signal. This tells me that if my source, first of all, if my source is ideal, then I don't have this R signal. If I don't have this R signal here, then this fraction becomes unity, then my Vx and Vsig are the same. It doesn't really matter what would be my input impedance, right? But if my V signal is not ideal, which is the case in real world, I'm going to have this R signal. And because of that, I want to make sure that my Rn is as high as possible. I want it to be infinity ideally. Okay? How about the output impedance? The output impedance is the perspective of my load resistance is from that perspective. So whatever load resistance sees this thing. Well, it's more than a resistor now, right? Because we talked about amplifiers and we said that amplifiers are kind of like voltage dependent voltage sources, right? The voltage that we expect to appear at the output here at this point, we like it to be K times Vx, right? Or sorry, I defined gain as A, so let's write it as A times Vx. So we want the amplifier to simply multiply whatever is happening at the input by number A, and that should appear at the output. But then, like any other real voltage source, we're going to have an internal resistance. We're going to show that internal resistance as R out. So my RL is going to see a source with an output resistance, R out, and the source is going to be a Vx, right? Therefore, I can say that, well, this is my V out, and this is my V out. I'm going to call that, well, V out. And V out is going to be equal to RL over RL plus R out times AVX. Okay, so this tells me that if I want the majority of AVX to appear at V out, I want this fraction to be unity, therefore I want R out to be ideally 0. Okay, or as small as possible. I can combine these two and write V out is equal to RL over RL plus R out times A times what was Vx, which Vx was Rn over Rn plus R signal times V signal. So now you can see the importance of R in and R out in our gain calculation. So for a common source amplifier that we have seen in the previous slide, as long as I don't have, so like basically the input impedance of a common source amplifier, as long as I don't have any anything connected to the gate, like a biasing resistor or anything like that, as long as I don't have anything like that, well, the current going to the gate is going to be 0 because, well, it's connected to a capacitor, and that capacitor is kind of like an open circuit. So this current is going to be 0, therefore Rn is going to be infinity. So this is nice because, like, even if I look at the small signal model, because we said that R in and R out are small signal model parameters, I can see that, well, V in is connected to an open circuit, a gap. So I can say that the impedance is infinity. While in the BJT case, we had an R pi here, and that was our input impedance, right? Our input impedance of a BJT common emitter amplifier was just R pi. Now we don't have this R pi, therefore it's just infinity. It's plain and simple. Now, in terms of R out, what we need to do is actually the same thing that we did with any kind of Thevenin calculation of any Thevenin equivalent resistance. First, we turn off any independent signal source. You know that the symbol V in, it really means a signal source to ground called V in, right? First, we need to turn that off, so we connect this node to ground. And then second, I'm going to connect the test Vx to the output here, and I'm going to basically call the current coming out of this Vx Ix. And I'm going to calculate the relationship between them. Well, when I have V1 defined as the voltage between this node and this node, they're both ground, so V1 is 0. Therefore, GM-V1 is 0. So this current is 0. RO or R0 is actually connected to ground, so I can actually draw it this way. And you can see that I don't have anything to the left of this red line, right? All my circuit is actually to the right of this red line. To the left, I have an open circuit across this current source, and the rest is just nothing. So I have just RO in parallel with RT. So I can say Vx over Rx is simply R0 in parallel with RT. And that would be my output impedance. Of course, we're going to solve more examples, and we're going to see that this is the simplest possible amplifier. This is for the case that I have just an amplifier like this. So V in is connected to here, source is connected to ground, drain is connected to some RD to VDD. But definitely, if things get more complicated, we're going to have a more complicated kind of input and output resistance. We're going to talk about it in future slides.